And here we are in the lab again. Welcome to episode 19. So it's what we're going to do today is we're going to work on the front end. And I know the front end's a long one, but we're almost there. And so I made I made a change to where the enable for the buffers, it used to get tied to the board select line, and I didn't like the way that looked after I thought about it, how it's going to work. So now the chip enable for the SRAM enables the buffers at the same time. So it's basically a transparent read and write through the buffers. You don't even know they're there. So then that leaves the board select is by itself. It just goes from the decoder output through the jumper that we select board number with, and it goes directly into the microcontroller and causes an interrupt. So then I'll go over that with you on the schematic, and then we're going to go dig deeper into the front end and pretty much wrap it up. But the next video will wrap up the front end as far as I can tell. So let's get to it. Okay, so I took and separated the output enable for the buffers from the memory select or the board select signal, whatever you want to call it. I haven't really named it yet. I probably should do that. So now it's tied directly to the chip enable. So the chip enable, with it connected like that on the chip enable, it just makes it so it's just a normal write. When the microcontroller uses our read write functions to write to the SRAM, it just goes directly there. There's no other requirement. So then that leaves the board select signal going to the input pin by itself. It's not connected to anything else. So that's RE1, port E1. And so this will generate an interrupt inside the microcontroller, and then we'll do something based on that interrupt. So that's what I did there, just to separate those. That is an official design change that will go into the next revision. So now let's go to our code, and I'll show you what I did there. Oh, and I did add one thing here. So I added a test point right here on pin 47. And if we go to the PCB, then it's just a bare pad that we can put the scope probe on. And in order to do that, you have to add it into the library as like a package, a part. It sucks that you can't just plug down a pad and connect it, because you got to do it in the schematic first. So the schematic, in order to connect to anything, it has to be a component. So anyway, I added it in there, and there's now a test point here, and that is the heartbeat. So now if we come over here to our code and come down here to our main function, past initialization code, and down to our heartbeat. So that I'm using the bitwise exclusive OR. That, according to ChatGPT, that is the fastest way to toggle the bits, the bit of RC9. So that is just creating a square wave on the output for our heartbeat, and that's a permanent. that will not be changed or go away unless we have to. But there's that is the official heartbeat that goes to that test point on the PCB. Okay. And I had to add one of these. I got to tell you about this too, because you're supposed to do a dummy read whenever you read from the PMP. You don't have to do a dummy write, but you have to do a dummy read. And you have to, the reason you have to do that is because the way it's buffered. You have to check the data sheet on that if you want to know more. But that's another thing. ChatGPT said, if you're only using 8 bits, you don't need to do this. But I wasn't getting anything going on here until I did this. So one of us is wrong. And this works just fine. And I've always done that in the past. So I suspect this is the way you have to do it. So from now on, that's the way I'm going to do it. All right. And then one thing that I changed, and I didn't mention in the last video, is when you do the double or the dual buffer mode, there's a PM write address and a PM read address. But if you don't try to use the right address here, it doesn't work. So that's how that has to be. So that catches you up on everything. Oh, and so when I have it set now, so when it boots up, it reads address 2 just one time, and then it displays it on the LED port, and then it runs the main loop. So it's not continually reading or anything. It just does it one time. It just reads what's an address 2, puts it on the port. All right. So then I have MainBrain already wrote to that data to that address, which is should be 56, hexadecimal 56. So when we boot up, we should see hexadecimal 56 on the LED port. All right, and that's everything in the main function that I changed. So then we come over here to the interrupt, and all I did is add in the interrupt for port E1, RE1, which if we go over here, should be for our address, our board select, which is, that's right here, RE1. All right. So this is the interrupt for RE1. So when RE1 comes through here, we set the LED port to 78. So initially the LED port's going to be 56, hexadecimal 56. And then when an interrupt occurs, it's going to change to hexadecimal 78. Okay, so this is the way it looks when it boots up. You can't power cycle it and have it read the right value, because when you take the power off the SRAM, that scrambles it to the reset state or an undefined state. And so then when MainBrain boots up, this board, our IO board, might boot up before MainBrain. So it would read the bogus value before MainBrain writes to it. So is what I'll do is I'll just go into the code and then I'll reset it. All right. So that's being held in reset. I'll release reset, and there's our 56 right there. So then we're going to cause an interrupt. If you notice the jumper over here is on the second address. If it was on the first address, it would send the low signal into the microcontroller. So we don't want to do that. But if I take and short these two together, it'll cause the interrupt. There you go. And that's our 78 right there. 78 hexadecimal. All right, so that's the final test for that. So now we can move on. Okay, so we have a basic framework to transmit data back and forth between main brain and the peripheral boards. And so, and we've proven that it works. Okay, so that's like a good step right there. So now it's time to go up one more step, and we're going to develop a command structure so that main brain can control the peripheral boards and exchange data back and forth as needed, at will. So in order to do this, I developed what I call the I/O cycle. And so the I/O cycle is the process of where main brain selects a board, sends it a command, the board acts upon that command, sends some data, reads some data, and acknowledges that it has received the command and it's completed its I/O cycle. And then main brain deactivates the board and can move on to another board, because no two boards can be on the bus at the same time. And each board has its own memory space in the SRAM, and no two boards can occupy that memory space at the same time. And part of the structure is that there's 8 different addresses that main brain can send out onto the bus. Now, address 0 is just a 0 null address where nothing occurs. No board is selected, no data gets transferred, the bus is idle. And so that leaves 7 more addresses for the board. So we can have 7 boards total in the system. And each board has its unique number or address. So that is the basic idea. And so I'm going to throw up a block diagram and we'll go through that and show in more detail how it works. So let's get to it. So at some point, main brain is going to need to exchange data with one or more peripheral boards attached to the system. And this is the beginning of an I/O cycle. So the very first thing that has to happen in an I/O cycle is that main brain has to write any data that it wants to send to the I/O board. It has to write that to the SRAM. And it has to write to the specific location dedicated for that specific peripheral board. Okay? So then once the data is written, main brain has to write a command to instruct the peripheral board to perform some function. And that command gets written to the peripheral board's address 0. Okay, memory address 0. So then, once the data is loaded into the SRAM and the command is loaded into the SRAM, then main brain issues an address onto the bus, a board select address. So this 3-bit address hits all the decoders of all the peripheral boards. And the decoders all split this 3-bit address into 8 separate board select lines. Okay? Now, that means there is 8 possible address lines, board select lines. However, board select address 0 is reserved by the system, so that when the address is 0, the system is idle and no data is being exchanged and no board is being selected. And that's considered the idle state. So then that leaves 7 possible combinations of board select lines. And that's why we can only have up to 7 peripheral boards attached to the system at one time. Every peripheral board has a board select jumper. And this jumper selects the board address or the board number. And every board has to have a unique board number. No 2 boards can have the same board number. Now, as the board select address is decoded and split into the 7 board address or board select lines, the board select jumper routes one of those lines to the microcontroller, and an interrupt is generated internally. Once the interrupt is generated internally, the microcontroller of the peripheral immediately reads address 0 for the command. And then it performs whatever action the firmware is configured to perform based on that command. And then any data that needs to be read back into the microcontroller from the SRAM is then read into the microcontroller. Once all the data is read and stored in the microcontroller, then the microcontroller has to write any data that it has to the SRAM. When all the data has been transferred and there's no other operations pending, then the microcontroller of the peripheral activates the acknowledge signal, which tells MainBrain that it has completed its part of the I/O cycle. And when MainBrain sees the acknowledge line go low, then it changes the board select address to 0, which deactivates the board select line. And when the microcontroller sees the board select line go high, it deactivates the acknowledge line, and the cycle is complete. So then there's one more part of the cycle, and it's called the halt. It's like an e-stop. So whenever MainBrain decides that the I/O board has to be stopped from doing whatever it's doing, like an emergency stop or some kind of an issue where it has to stop the board from its operation, then it will enable the halt signal, and the halt signal will cause the I/O board to stop doing whatever it's doing, and we'll define that in the firmware. But it's like an e-stop. Like if you were like controlling a machine and somebody hits the e-stop, then MainBrain would issue that halt cycle, bringing that halt line low, and then the I/O board, the firmware, has to stop doing what it's doing. Okay? Okay, so that's the basic idea of an I/O cycle, transferring data back and forth between MainBrain and the I/O boards. So now we need to develop a command structure to send commands to the board to get it to do what we want it to, and then the board will send status information back, data and status. So this part of it's going to be an evolving, ongoing development process. It'll have to get changed and molded into our needs when we develop our data acquisition part of the board. So, and that's coming real soon. Uh, so let's go to the code and I'll try to explain how we're going to do the commands the best I can. Okay, so let's start building a framework based upon that IO cycle block diagram. All right, so we're looking at this through the eyes of the peripheral board. All right, so the first thing the peripheral board sees is this interrupt over here from our board select line. All right, so when that line goes low, it generates an interrupt. It comes in here. And the first thing, according to the rules of our IO cycle, is that we have to read memory address 0. All right. So we come over here and we get our memory read function. All right. And we read address 0. All right. From the memory board's perspective. And so then when we read that memory location, that's where the command is kept. So we have to do some kind of a branch based on the command. So is what we'll do is a switch function. And that's going to switch based on this mdata, which is the variable that we put the data in. When we read the data, we put it in this mdata variable. So we're going to do the switch statement based on that. So the first thing is case 0. That means when this mdata is 0, we do this, and we're going to put a comment in here. So that'll be command 0. And then we won't put any code in there yet, but we will do a breakout here. And then we will do another case 1 and do a note for command 1, and we'll do a break. Now, so we don't have to write all 255 because this is an 8-bit variable. So there could be 255 unique commands in there. And we'll add commands as we need them. So we don't want to just write out 255 commands. We might only have 10. It's hard to say. So we'll do a default case. And we'll just call that default for right now, and then we'll break it. All right, so then any number that is not a 0 or a 1, that doesn't match the case, then we will put it, oh, I forgot that. Then it will bypass and go into the default and then just break out. All right, so then all numbers, technically all possibilities are handled right there. All right. So we'll write our code for the commands later. But the first thing after the commands, after we read address 0, then we need to, the commands will take care of reading and writing any necessary data. So we will just terminate with an acknowledge. And so as you've seen in the block diagram, the acknowledge line terminates the cycle. And let me show you the acknowledge here. So this pin 12 used to be PA13, and I don't even know how that got in there. That's from way back, and there's no PA13. Uh, there's the SRAM doesn't have a PA13, and on the mainbrain side, it just goes to the main microcontroller on mainbrain. So I renamed this for the acknowledge, and it goes to RE5. And so we have to configure RE5, and we'll do that up here where we configure our other SRAM stuff right here. So we'll come down, and just before we do the heartbeat test point, we will do the acknowledge. Okay. And so that is RE5. So we got to make it an output. So we go triz E bits dot RE1, and that will equal a 0 for an output because we're going to pull that line low. And so we're going to have the default value as high. So we'll put port E bits dot RE1 equal to 1. All right. And so that sets up our acknowledge. Okay. And so while we're here, we better handle the halt. So we want the halt to be an input. And oops. And so it's active low, but we just want to configure it as an input. So we got to figure out which one it is. So I made this one the halt pin down here. It used to be the reset, and tying the reset together so everything gets reset at the same time, it didn't work to my satisfaction. So I just made this the halt, and it goes over here to RE9. Okay. So we'll go back to our code. And I don't think I ever configured any RE9s anywhere. Just to make sure there is a 9 prototype. Oh, that's our data direction bit that we're using on our prototype. That's right. So we won't do anything on that right now. Okay. So we're running without an e-stop. Not a big deal. Not a big deal at all right at this point. So we'll forget about the halt right now. We'll come back over here. And so we got to do our acknowledge of the cycle. So that is RE5. So we want to when we want to send an acknowledge, then that's port E bits dot RE5, and we can use the slower way here because I don't think it's going to be critical in this for time in this particular interrupt. So we'll bring that low. So now we're going to change this interrupt here so it will interrupt on both the falling edge and the rising edge of the interrupt. So, and because like we've seen in the block diagram, the mainbrain brings this line low, this RE1 line low, when it selects the board, and it stays low. Okay, so it stays low until mainbrain receives this acknowledge signal, and then it brings it high. So we want an interrupt on both. All right. So it's what we want to do is use an if statement to check to see if RE1 is low or if it is high after the interrupt occurs. So we're going to use a bitwise check here. to determine that, since we want to use kind of faster stuff. All right, so we want to take this. So if it's low, we want to perform this action right here, all the way down to here. All right, so we probably just want to move that over like that, and then get our bracket in here. All right, so when the interrupt occurs, then it checks to see if it is a rising edge change on port E1, RE1. And then if it is, it's going to check to see if E1 is low or high. So in this case, it's checking to see if it's low. Let's put a note. Check to see if RE1 is low. All right. And so then it performs our thing and sends the acknowledge out. All right. And then it clears the flag and goes. But we need to check to see if it is high. Because if it's high, then that means this has already occurred. So I'm going to paste that in there. And line everything up. And then we're going to perform the action and then exit. All right. And now the action is, so we have to take this out right here, because we want to make sure that it is high. And then we'll perform the action of bringing this one high. That's all we need to do in that case, okay? All right. And we'll make that a 1. And that should be our complete interrupt, all right? And that should be a complete I/O cycle from the point of view of the peripheral board. Okay, so there you go. We have a basic framework for sending commands and transferring data to and from the peripheral boards. And we're set up for multiple boards somewhat. Later on, after we get our new revision boards, because we don't have our base address jumper on this prototype board. So when we order our new boards down the road, then that'll be incorporated in it. And then we'll assemble 2 of them, and we'll stick 2 boards in there and see how they work. And maybe we'll probably write some code for that. But right now, we are done with the front end. We will add commands to the command structure as we need them, as we develop the data acquisition part of the board. And so, yeah, it's time to move on. The next video is going to be probably the digital potentiometer. And I'm kind of excited about getting into that. And it's been a long one, but the front end is working good. We got good code. We got a good foundation. And so, yeah, that's it for this video, and I will see you in the next video.